Good morning, everyone. Honorable Speaker, respected HOD, respected professors, dear students, I welcome you all to the webinar Pursuing Quantum Career in Age of Neural Networks. To begin with, I would like to request Dr. Prince Ganai to welcome our Honorable Speaker and other participants to this webinar.
Thank you, Niklesh. It's my pleasure to welcome you all for this wonderful lecture. I understand that this is going to be a very absorbing lecture because I also, was quite interested in actually interacting with the speaker on this very important topic that is some quantum computation and some sort of this kind of thing. I welcome speaker. I understand he's one of the very bright students we have from our valley and is now in IBM. And I have interacted with him a couple of times, and he has been always wonderful in his understanding and thoughts. I hope that all of you will have a wonderful time with this fellow. And I also welcome my colleagues, all very active colleagues, and my dear students. Thank you very much. And I hope that it will be a very good experience for all of us.
Thank you very much, sir. Now to give the introduction about our Honorable Speaker, Dr. Rukhsan sir. Dr. Rukhsan is a quantum artificial intelligence scientist at IBM, former time series forecasting analyst at Johnson & Johnson, former postdoctoral fellow at Zhejiang University, China. He is also the founder of KIMS, Kashmir Institute of Mathematical Sciences. He has a research experience for more than 10 years in quantum computation. He is an international speaker and also the co-author of Huck-Kaufman algebra that is used in quantum mechanics. Now I would like to request Dr. Rukhsanul Haq sir to greet us with his wonderful lecture.
Yeah, hello, good morning, everybody. So, yeah, first of all, I would like to thank you all, especially Professor Prince sir and Professor Rubab for this very nice invitation to actually the program was to come down to NIT, and I would have really liked to interact with you personally. I have been to NIT only once before when I gave a talk maybe many years ago, around 2015 or something. So that would have been the ideal condition, but because of the some technical difficulties, COVID related, I think we will still manage. Okay, so let me get started. I will share my presentation. Just give me a moment. So Nikhil, is it visible, the screen?
Yes, sir, it is
Yeah.
visible to us.
Okay, cool. Okay, so yeah, I mean, what we will do, I mean, this is my suggestion would be I will go through the presentation. I will not take much of your time because we wanted to keep this session interactive. I would like to really listen to the or take the questions from the students. I think that is the main motivation of having this session, to see what the questions or the concerns or maybe confusions also which the students have, and try to address those questions. But before that, I wanted to have a little bit of a presentation. So okay, so this is the overview of presentation. What I'm going to do, I'm just going to keep it kind of more or less non-technical, because I don't want to barrage you guys with technical details. They will come later on when anybody gets interested. We can take the technical details later on. But what I'm going to do is going to give you an overview of what is happening in these industries, which is like quantum computing as well as the data science. Maybe you guys are not so much involved, you don't listen to the news or all that, but because all of us live in 21st century and these technologies do make an impact on our daily lives, forget about the bigger impact on education, on business, on economy, and healthcare and whatnot. So I would like to take a sneak peek and just walk you through these developments, because I'm personally involved in these things. So I may be a little better informed than you guys. So that will be the one thing, and I will do it in both data science as well as in in quantum computing, and then we will talk about what is it that if we are convinced that quantum computation as well as artificial intelligence or deep learning, so to speak, are important, then how should we get involved, especially the youngsters who have to choose a career ahead? So how should we get involved? What should we do about it? So okay, so I wanted to get started with a personal note. This is myself standing in our Johnson and Johnson office, Bangalore, and the anecdote is following. When I shifted from physics to industry, so many of my friends thought, okay, this guy used to tell us that I am very much passionately interested in physics. Now he's leaving physics and going somewhere else. And maybe I don't know what kind of impression they would have got. But I wanted to tell you right at the beginning, that's not a story. That's not how it is. You don't need to leave physics. I mean, I will never leave physics. Physics is my first and passionate interest. I mean, I will never pay a cost of leaving physics to do anything. Okay, but the good news is following, that you don't need to leave physics to do data science or to do any other thing. In fact, I would convince you that being a physicist, being the knowledge or the background from physics is a strength of any person who wants to shift to data science. So I would say even the data also tells us that if you look at the statistics, the number of people from physics who shifted to data science, they did pretty well as compared to the ones who are from computer science background, or maybe mathematics or physics or statistics. So the data suggests that's why there is a kind of a lot of huge inflow from physics community or physics graduates, they shifting to data science. And this trend is not only in India, it has been seen in every country. Especially, I mean, you would see lots of articles talking about physicists going to Silicon Valley and then winning over there. It's not just that you go there and become a loser. It's like go to the Silicon Valley, go to the data science, and then win over that data science. I mean, make it your own. Okay, and on the right side, you will see some of those areas in which I have worked over the last maybe 2.5 years. These things will come along as I go along in the presentation. But the main message which I want to give in the beginning is that it is not that anybody has to leave. I am still a physicist, and I will always remain so. And even then, I mean, I keep on doing machine learning. That is never a barrier. Physics is not a barrier. Physics is one of the best things to have as a background for any person wanting to shift to data science or any technology, I would say. So 2000, let me take you to 2016. Things were just maybe there is this author, he's writing a very interesting article in New York Times. He's just summing up what is happening. So Google, as we know, it's a part of our daily life. And Google started as, what Google gave us is a search engine. And they wanted to build their business around that. Search algorithm is what they discovered. But they realized at Google that they are not going to survive by just using search engines alone or some other software products, or Gmail or Google Hangout, Google Meets. This is not what they are going to, they cannot survive. Their business cannot survive on that. So they did there was a rehearsal, there was a kind of a transformation within the Google. What they did is that they adopted AI, and that is the awakening that's happening. The Google as a big industry realizes that AI is important. They embrace AI, then they move on. And now we have in some sense new version of Google, and now we have the Google, and Google is still with us, and hopefully it will remain so. So what has happened is that there is this so-called rise of neural networks, and it didn't happen in 2016. It has a long history, but 2010 onwards there are big jumps there happening. Okay, and there are a lot of strides which are happening, and the reason for that is the computing power, which has become so, I would say, cheap. Nowadays computing power is very cheap. You can, and now people have access. I mean, I have friends who have access to GPUs in their laptops, so it is not so difficult to buy, and affordable for even PhD students to have access to GPUs. So therefore, I would say this rise of this access or the computing power becoming cheap is one of the reasons that neural networks are emerging more and more, because we need a lot of computational power to train these neural networks. Okay, but the thing is this, we cannot deny this fact that neural networks have already there's already the rise of these neural networks, and they are already, I will also convince you how they are part of our lives, daily life, without realizing that. You guys, all of us are using neural networks in our daily life, even if we do not realize that. So let me bring you back to physics, from Google to physics. 2020 was a very interesting year, especially for those of us who have been fans of Roger Penrose. Roger Penrose has been a great fan and fascination and idol for me. I have always loved his work, and so do many of us love his work on quantum gravity. But they told us in 2020, Roger Penrose got Nobel Prize for discovering that black holes exist as solutions to general theory of relativity. That surprises us, because the Professor Einstein, who discovered general theory of relativity, did not get Nobel for discovering general theory of relativity. How is it possible that anybody will get Nobel Prize for just working out the solution, some interesting solutions of the theory? Okay, now let me tell you the another part of the story. Another part of the story goes back to this particular image. 2019 April, you remember there was this image which came, and a big sensational news. With the news came that the first image of black hole has been taken, right? And this news was all over the places. It got a huge press, and deservedly so. And this was really interesting and a huge moment in the history of physics. Fine. Now we will dig a little deeper. How is it possible that this black hole, which was kind of captured in image millions of light years away from us, how is it possible that somebody was managed to take a picture of that black hole? Fine. So you will discover that this person whom you see in very excited and happy in this picture, her name is Katie Bowman. She played a lead role in making sure that the world has the first image, so to speak, the first image of the black hole. And how did we manage to get that? And that the first image of the black hole is somehow related to, I mean, this is speculative, but we cannot convince that any theorist will just get a Nobel Prize without any experimental confirmation of his theory. So what happened is that people have been doing experiments. I think 2009 onwards, they were from these laboratories. There are different laboratories throughout the world where they have giant telescopes. They are getting the data from these from the astronomical objects, and you see in this picture itself, you have these EHT telescopes, and they are placed in different places. I think 8 different places in the world, and they are getting this data. And this data was being captured from 2009 onwards till 2017. And in 2017, they started doing this, starting working out these pictures. And what they were doing, so what they were doing, they were using this, first of all, capturing the data. Then there was something happening. What was happening is that AI was being used to get to that image. As you can see in this simulation, which I have taken from the Nature paper. So the data, you see the data is being captured. That data, which has been collected over many years, I think almost a decade, they have captured this data, and that data was fed to a something called a convolutional neural network. It's a neural network which you use to process the images for the computer vision. Okay, so this data was sent to the neural networks, neural network models, and it is the neural network model which gave us the image, not the human. And for humans, it is not possible. Okay, but what humans did is that they very meticulously, they put a lot of hard work to make sure that we are getting the data, and then finally that model, and the Katie Bowman was the person who was leading that effort to running those models, running those neural networks, AI models, and finally getting us that image. So otherwise, the difficulty of getting this image, like you see from the Mars, on the Mars somebody is showing you a small, maybe a small bread kind of a thing, and then you are taking using a camera from here and trying to capture that that small objective on the Mars. It is so difficult to capture the image of black hole from Earth. Okay, so this is a first amazing example. I mean, I personally got so impressed to see that the impact of neural networks, impact of AI in the discovery of the physics. I mean, we are not talking about AI is being used in no technology. We are not using and something which we may not be directly related with. We are talking that AI is being used in the discovery of the physics, in discovering, in understanding more about black hole physics, in understanding more about the results of the general theory of relativity. So in that sense, physics has fundamentally changed. That is something which we have to realize, that it is we do not, physics is not being done conventionally as of now. I mean, this particular discovery of getting the black hole image would not have been possible without the intervention of the deep learning. No AI, no deep learning, no neural networks, no image of black holes. End of the story. That's it. We would have been left here on the planet Earth just doing our calculations without ever getting to the proof of general theory of relativity. Now let me take you to somewhere else. Let me take you to Cern. What is happening in the Cern? Cern, I mean, we know a big discovery happened, and that led to the Nobel Prize of Peter Higgins and other people. And so what is being done in, let us first of all look at the data which Cern produces. Cern is let me tell you, you would have heard a lot about something called big data, people talking about. There's a lot of hype about big data. I am telling you, physicists at Cern are already solving big data problem. They are solving a big data problem which is much, much bigger than people in industry will solve. What is the size of the data? The size of the data is, it is 300 petabytes. We are not talking about gigabytes. They have 300 petabytes of data, and this is few years ago. The slide is few years ago, okay? And now, I don't know, it will be bigger than that. Now you have 300 petabytes of data, and you have to discover the particles from that data. How on earth are you going to do that? How is it possible that one physicist will do that? How is it possible even 100 physicists will do that? You cannot do that. I mean, physicists will not be able to do anything with that data without taking help from neural networks. Okay, and that's exactly what Cern is doing. I am just showing you some of the images, but let me also tell you, Cern has again and again publishing these challenges, machine learning challenges. And interesting, one of the challenges was maybe published in 2014. What they do is that they give you the data, and then they invite you. Then they say, okay, you come and work on the data. They will give you prizes. I think in 2014 or 15, the prize was not won by a physicist. So the person who is giving us these particle classifications are not always physicists. It's not the physicists who are telling us that a new particle has been discovered, this particle has been discovered, or some new property has been discovered, or new symmetry has been discovered. It's not always physicists. It is any person who is good to do data analysis, who is good to run these machine learning and deep learning algorithms. They are the people who are leading the discoveries of physics here at Cern. Okay, and now let me tell you, you see many things over here. You may not be familiar with that. I just want to tell you on the left side image. So what this data is being, where is this data being put? These are some called modern, very, very high scalable data, something called a database systems. One of them is Spark, one is Hadoop, one is HDFS, and all that. So they are like in industry, in top class industries, like is Google, Microsoft, IBM, any company, they are using these databases. Okay, Spark is the one which people typically use in data, and Cern is already doing all these things. And I think they were doing these things with, definitely they will be doing it in collaboration with these industries. In universities, it's not possible. In universities, we don't have people who know even so much of sophisticated knowledge of databases, how to manage with databases. You have to get industry involved. Fine, but the thing is this: what is to be known are two things from this slide. One thing is that LHC, the big discoveries which we make at LHC, they are not made by physicists alone. They are made by physicists, then help from computer scientists and other people, and with the help of neural networks. Without neural networks, we will not be discovering any particles at all. Okay, and this gives us one more realization of how important neural networks have become in modern. Not only in, I'm once again saying, it's not about technology. It's not about somebody, Facebook is taking data from you and analyzing. It's not about other things which we will discuss slightly later. It's about the fundamental discoveries about nature. Fundamental discoveries of nature are happening in collaboration with the neural networks. And I would say, I would rather argue, it is not possible without the help from neural networks. Let me just give you a bit of a more kind of a picture of what's happening at Cern. What exactly is happening? So you see this, we have the data collection which happens from Atlas, Alice, and CMS and other detectors. Then that's being registered. That job is done by physicists. Then we have a raw data there. Then that raw data goes through a pipeline. It goes through a processing. Then a lot of data analysis happens, a lot of data analytics happens on top of that. And at the end of the long process, you have the final results. Okay, so there are two pieces. One is the experiments which are done by physicists. Then there's a huge pipeline through which the data moves, which is done by neural networks or other people, data analysts, data scientists, and other folks. That is the pipeline of the discovery of big discoveries which are happening at Cern. Okay, so let's keep going. And now I want to take you, bring to our daily life. Any one of us is using, whenever we have to buy some stuff, we go to an Amazon. And when you go on Amazon or Flipkart or any e-commerce website, what you do is that you buy one let's say book or a shoes or any item you buy from the Amazon. What Amazon immediately tells you that because you have bought this thing, you may be also interested in a few more things. Okay, and then sometimes we buy that, sometimes we don't buy. But let me take you to now Facebook. On the Facebook, you see you have these friend recommendations coming in. You go to the YouTube, you watch one YouTube video, you get 10 more recommendations about that. And many times you see when you like one, you also among the 10, you also like 2 to 3 videos which are being recommended to you. Okay, then on Netflix, I hope many of you who are watching Netflix, you watch a movie on Netflix, and then 3 more or 5 more recommendations are given to you, and you many times you like those movies. Fine, what exactly is happening here? You will be amazed to know that the stuff which is happening behind YouTube, Facebook, Amazon, Flipkart, Netflix is a very simple problem which all of you will be able to solve. It is using something called a matrix factorization, and many of you may be familiar with something called a singular value decomposition. The first recommendation engine was built by Netflix, and they used singular value decomposition, which is not difficult for anybody from physics community, for any person who has done a bit of a computational physics. It's not difficult for anybody to do that, and that SVD is running these recommendation engines. So what you see is an application of what you would have learned in computational physics. That is, so the tools wise, this is same, but the effect which it produces on you when you go on Amazon or Netflix or anything, it's amazing. Fine, but it's not difficult. Similarly, now we come to another application of neural networks. You open your phone, you will see on your phone there is this Google Now. You can just click on that mic and you start speaking. You say, play this thing for me, play that thing for me, or you can start interacting with it. So what is happening is that there's a neural network. When you click on that mic with the Google Assistant, which is embedded in your phone, is basically when you click on that, it starts taking your voice data, audio signal, and then it starts recognizing what that audio signal is. So that cannot be done by Google. There is nothing in that phone which can do it, except for a software, except for a piece of code which runs a neural network. So what is happening is that something called a speech recognition. So, and that speech recognition is happening by a neural network which has been embedded there, and Google has one of the best speech recognition algorithms, so they are using the Google. Okay, similarly we have lots of stuff happening, like as you write a mail. Okay, when you start writing your mail, many times it corrects. I mean, nowadays I don't correct my spellings. My email editor always does it, or any editor I use, it always, I do not have to bother about my spelling mistakes. It always corrects itself. It auto corrects it. And then same is true. You go to the Word, you go to any place, there's auto correction is always there. But how do the auto correction work? Auto correction works on something called a natural language processing. These neural networks have become so good that they have started understanding natural language. And if you believe the linguists like as Noam Chomsky or Steven Pinker or people like that, they are telling us that understanding language, natural language, is one of the most challenging tasks for any person, any non-human object. Okay, any non-human agency, it's going to be difficult. But here is the thing. Natural language processing is something on which neural networks have done amazing progress recently. In 2019, in 2020, if I tell you what neural networks are doing, you will not trust me, simply speaking. So if you just go on Google and try there is something called from OpenAI. OpenAI is a company to which I think Elon Musk was also related. So OpenAI has released something called a GPT-3. GPT-3 is a language model which understands language. And this GPT-3, not only is it that it understands language, it can write its own poetry, it can write its own composition, it can write its own articles, it can write a lot of stuff. You just have to give a title to that GPT-3. There are problems though. I will come back to those problems later on. So this is where we are. I mean, if we look at last 2 years, there have been amazing developments in natural language processing, and that impresses me more because, honestly speaking, from a scientific point of view, it is true that understanding language is not easy. Language is a very, very complex phenomena, and understanding for any computer program, for anything which we do on computationally, it's not so easy to kind of understand the language. Forget about language generation. I'm saying GPT is also doing language generation. It's writing its own texts. Fine. So therefore, this is really tremendous, and it definitely begs the question: what exactly is going on in these neural networks? And if this trend remains so, what will happen to us in future? Okay. And many people are really concerned. Elon Musk is one of them, but we will come to those things because his concern is something different. But we will come to that. Okay, now let me take you to some another problem where neural networks are doing once again great. So the problem, which has been more or less the open problem, is like all of us know the stock markets. Stock markets are crazy. They are so crazy. I mean, you don't know what's going to happen next minute. Fine, and it gives high blood pressure, hypertension problems to those people who are in stock market. Okay. So how do you solve this problem? And this is being so difficult. Is it possible that AI can come in and help us? So I would not say that AI has helped us to solve the stock market problem. That's really, really difficult. It's in physics language, it's a non-linear dynamical phenomena with so much of complexity that it's really, really difficult to solve this problem. It's very similar to turbulence problem, which we have in Navier-Stokes problem. In hydrodynamics, we have this turbulence problem, which is one of the open problems. I can more or less think of stock market of the same complexity class. We cannot definitely beat the market here. However, with time series forecasting, we can do a lot of things. Neural networks have really done amazing with time series forecasting. Now, time series forecasting is everywhere. First of all, in Kashmir, we always worry about weather. So it's a time series forecasting problem. So I don't know our MIT department, our meteorology department, whether they use AI or not. I'm not aware of that, what kind of models they're using, but it will be really helpful if we want to improve our weather forecast. It will be really good to have AI models running those weather forecasters. So, but I was myself involved in this was one of the first problems which I solved, which I worked on when I shifted to industry. And we use it typically. People use it to use something called a statistical models. They were built by statisticians long time ago. And what we did is that we changed these models. That's the trend now, that you change the models, go from statistical models to AI-based models, neural network-based models. And yes, we did observe that there's a lot of improvement when you go from statistical models to AI models. But the best thing what we did is that we wanted to combine both the models and create something called a hybrid model. But let me give you a flavor of what kind of problem is it being solved. We know, I mean, you will be very surprised to know that typical a standard problem in time series forecasting is the same problem which we solve in statistical mechanics, which is a Brownian motion. Usual your time series data, it's a random these are like random numbers, though they have a pattern, but it's a random number. It's like a random motion, and as we have in a Brownian motion. And our job is to take this data and use the model. The model has to basically learn the information in the data. And where is the information residing? Information is residing in something called a temporal correlations in the data, because this is time series data, and then the correlations live in the information lives in correlations. The model should be able to extract that information, and then it should be able to predict. It should capture the pattern in the data and should be able to tell what will come in maybe few days from now. And this is exactly what Amazon is using. Any e-commerce, any place where you buy stuff, they are all using these time series models. And I'm sure, because I have used it. I have gone through the Amazon time series forecasting models. I know what they are using. So they are using it. Flipkart is using it. if you go, I mean, outside, we also buy food, we order food. They are also using these time series modelers to make sure that the food reaches in time to you, and the home delivery, that process gets automated. Fine. So time series is that domain which is ubiquitous. It's everywhere. You use it everywhere. And then AI is the place where it has already made its mark. It is doing amazingly good. I mean, I think one of the models which we used to use was from Facebook. It's called a Prophet model. You can take a look at it. It's kind of a regression model, some neural network based model, and you can use that model, and it gives really pretty amazing results when it comes to time series forecasting. So I would say we have come very close to beating the stock markets, and one fine day, maybe we have that good news. But one thing is there definitely, which I have myself worked. I have done forecasting for Bitcoin. These cryptocurrencies nowadays, people are using Bitcoin and all that. I did prediction forecasting for that. And it's a very interesting problem. I mean, if you think it from a physicist's point of view, you are once again studying dynamical evolution. Like as we study in physics, we always have, whether you are in classical mechanics or in quantum mechanics, or you are studying quantum field theory, you always study time evolutions. Time evolution is the basic problem which we study in physics. Time series forecasting problem is the same problem, with a slight difference that the time which we are using is not continuous, it is discrete. You have these discrete time points, and then you are solving the time evolution problem. I think the reason why I did well, and I think I did this one of my project, it really worked well. I personally understand it this way. The reason why I was able to do better than my colleagues at my company was because I had this physics background, and those of my colleagues were coming from they were not from physics background, and I had this background from statistical mechanics, from classical mechanics, from quantum mechanics. I had done time evolutions all the way through my career. I have done time evolutions, and it was very easy for me to do these problems, and that's why I think this project worked so well for me. Now let us briefly take a look through. I mean, I just told you some of the amazing stuff that has happened recently, but where did this whole thing start? And was everybody thinking about neural networks? No. It wasn't like that. Let's go to 1920, 1940. There are two main people. One of is McCullough, and another person is Pitts. They were trying to understand the brain. They were trying to understand brain from more electrophysiology point of view. What exactly, how are these signals moving? What are the voltage fluctuations that are happening? How is the signal moving from brain to, from nerves to muscles? That kind of questions they were interested in. And they started trying to make a mathematical model, some sort of a differential equation. They wanted to do that in line with the tradition of that time. That time we used to use these differential equations and all that. So they built the first model of neuron. Okay, they were able to understand what they were able to understand, how, like in a neuron, you have this, it is in the stationary state, then it gets activated, then there's the electric pulse that moves, then it goes back. Fine. That thing was captured accurately by McCullough-Pitts model. Then the next big development happens by Rosenblatt. Rosenblatt was the person who built a so-called first neural network. It's called a perceptron. What it does is that it differentiates between the neurons which are firing, which are active neurons, and those who are not firing. It's like a classifier, a binary classifier. It just differentiates between the two, and it is the first modern neural network. But what happened at that time, as happens in many cases, there were these guys, Minsky and Peppert. They were like authorities of that time. When Rosenblatt tells them that he has discovered this thing and is doing these things, they were very dismissive of his project, and everything stopped there. There was a halt, what they call as a dark age in AI winter. There is not much development. People are just doing some theoretical results, but not much progress in terms of taking the neural networks ahead. But then something interesting happens in 1980. An important algorithm was discovered, which is called a backpropagation algorithm. So backpropagation algorithm is very important, the way neural networks learn, the way how neural networks learn. The backpropagation was very important. That was discovered, and then many things happened. And 2010, I think that was like a kind of, I would say, a revolutionary point, because on the one side, we had made more progress in understanding neural networks and controlling them. On the other side, computational power has become very easy. After that, many things happened. Two big events which they happened. One was the Watson. IBM developed this Watson machine, which is like the way you have nowadays Google Assistant or Alexa or Siri or Cortana. So similarly, IBM had developed this Watson. It was able to understand the natural language. or it was able to also use a chess. And then that time there was this I think this Russian player, I just forgot his name, but the IBM's Watson machine defeated that chess player. And that was like, this was like unbelievable for humans. How is it possible that this intelligent, so brilliant chess player, a machine, I mean ultimately a boring machine, how is it possible that it's defeating this human guy? Okay, but it defeated again and again and again. And then after that, few years from that day, there was another game which is called Go. And in that Go, I think it was the super master in that game was I think it was a Korean person, and that also was defeated by Google's AlphaGo. Okay, and these were like, no, they got us thinking into this, what exactly is happening with these neural networks. Then many other things happened on computer vision. There was object detection, many other things happened, started happening, and that got us ushered into a totally new modern era of neural networks. When people started to become more serious about AI, businesses became more serious, everybody became more serious, and that's where we are. We are right at the middle of this modern AI age, and it is, I am telling you, I being a practitioner of this, I being an AI scientist, I would tell you that no, that the future is going to be, every bit of our activity is going to get influenced. It's already getting influenced, but I'm saying it's even more so. Now let us shift to quantum computation for a moment. Okay, so I just want to tell you some important events that happen in the quantum computation, which you may not be, I don't know how aware you are, but 2019, by the way, 2019 was the same year in which that first image of black hole was taken. Same year, maybe towards the end of the year, this experiment was done by Google, and in fact the results were discovered, released, published in Nature. What they did is that they wanted to take a huge quantum leap, because there is this question: quantum computers are much better than, exponentially better than classical computers. They wanted to take a task and show that actually quantum computers have that power. It's not that they are doing 2 times faster, 3 times faster, or 5 times faster. They should be doing exponentially faster. They took a problem, something called Boson sampling, and it's a random sampling. Like, as you try to, in some sense, you have a data and you try to guess the distribution of that data. That's the kind of a problem they were trying to solve. And if you use the classical computer for this problem, it will take you lots of years. According to them, it will take 10,000 years to the fastest supercomputer. But with their machine, it was not a very big machine, just 54 qubit Sycamore machine they had, and it just took few minutes of that processing time to get that job done. Okay, and therefore it was a huge leap. I mean, it after that there is a lot of development around that. That quantum computers can actually, people are trying to use other tasks and make sure that quantum computers are, this is like it's a confirmation. It's a confirmation that quantum computers have this computational power. Otherwise, we have mathematical and theoretical arguments that they do well, and we have some experiments where they do slightly better than classical computers. But the Google's experiment was really important, because it more or less gave us the sense that no, the quantum computers really have this power and we can use them for many purposes. Okay, then 2020, what happened is that Amazon comes in and it also enters this quantum computation business. By the way, Amazon were doing, they are using a lot of AI because they are e-commerce giant. So they were using a lot of AI in their day-to-day business, but they were not in quantum computation. But they got serious, and then they started. I think they have developed a center in Caltech. In collaboration with Caltech, they have a center there for quantum computation. And then they come in, and they don't have their own hardware definitely, but then they bring 3 big hardware vendors. One is D-Wave. D-Wave is a Canada-based startup. They were the first to do something called quantum annealing. And then there's IonQ is another startup. They are coming up with the ion trap based quantum computer. Then Rigetti is another quantum computer. I guess it's also in Canada. So they now, what you can do is that you can go on Amazon. Not only is that you can buy other stuff there, not only is that you can start using their neural networks. It's by the way available. But you can also buy quantum compute. You can tell them, okay, give me quantum computation power for 1,000 rupees. And yes, you can buy that. In fact, you can, in the beginning, you can buy it you can just take it for free. Then you can say, okay, I just want to, and you can do a lot of sitting at your home. From the luxuries of your home, you will be able to run D-Wave, IonQ, and Rigetti quantum computer. As good as that it has become. So now you can see quantum computation is reaching You are not going to quantum computers. Quantum computation is coming to the doorsteps. As if it was not good, as if it was not enough, in 2021 January, IBM comes as a full-fledged roadmap for this more or less this decade. Okay, what they say is that already they have. I mean, IBM is already a leader in. IBM is an immense legacy in quantum computation. They have been doing. Rolf Landauer was with IBM. The person who discovered tunnel diode was with IBM. Phil Anderson was with IBM. Take a name, big name, you will discover that they have worked with IBM. IBM has a huge, immense legacy in the computation and physical sciences as well. But what happens is that I think, and similarly, teleportation, super dense coding was discovered by an IBMer. His name is Charles Bennett. Then teleportation was discovered partly at IBM by Charles Bennett again. So there is a lot of IBM is always involved in quantum computation. Maybe from 1980s on right from the 1980s itself. But now this decade, IBM wants to take it more serious. They want to say that 2023, they are like fully charged that they want to have 1,000 qubits ready by 2023, which is like a couple of years from now. Okay, and 2025, they want to go on to the race to have millions of qubits available. Just imagine when we are like a few years from now, where will the world be? What will be the world like? What kind of scenario will be in the world? What will be people doing? Like as this year, many of you would have taken the IBM quantum computing course. Okay, this is like a beginning of the story. 5 years from now, I am telling you right now, everything would have changed. Everything beyond your imagination. You would not even imagine what it will. So what this talk is about, what today's session is about, it is better to get ready now. Do not get late. You will not only be left behind, you will not find place where to stand now in this whole race. Where shall I go? So, and then now I come back to the earlier question, which I was saying, why is it that Google, Amazon, IBM, anyways, IBM has its own interest in quantum computation, but why is Amazon getting interested in quantum computation? I think this is an important question. Let me tell you now. I talked about earlier that GPT, which is doing natural language processing. This GPT language model can learn about. It can compose poetry. It can write. Some people say it can write code as well. It can write computer code. It can translate. You have a computer code in Fortran. You can get it translated into Python. You have into Python. You can translate it into C++ or C++ code. You can translate it into Python language. Okay, so all this amazing stuff is happening by these GPT and language models. But there is a problem. There's a huge catch. We call it computational bottleneck. You know how many parameters those models have? Not 100, not 1,000, billions of parameters they have to train, and then only it can do well. And that's why it's possible with OpenAI, it's possible with Google or other people who have huge computational resources available. For people like us, or even people like at universities, or maybe some research centers, it is not possible for us. We don't have so big computing machines. Even we at universities will not be able to run these things. Okay, then comes the quantum computation. Now, quantum computation has this promise that if you take these language models and you try to run them on quantum computer, whole thing will change. You will not have so many parameters to train, because quantum computers will save a lot of computational power. It is like, in some sense, we can run them. We can take them from billions of parameters maybe to hundreds, which is manageable. Okay, that is why quantum computation is important for these people. Otherwise, for Google, the main interest is AI. AI is which is running their business. Amazon, AI is which is running Amazon's business. They are not primarily interested in quantum computation research or even application. It is becoming important for them because it is making their AI, that quantum AI, what we call as quantum neural networks, they have the actual promise, and the future belongs to not to AI and not to quantum computing alone. It belongs to this happy married couple, which is called a quantum AI. Okay, that is where the future belongs. And this is just architecture of how it goes. You have a quantum circuit, and then you have a classical machine learning model. They are in sync with each other. And let me stick you with this. This is just a bit of a if you have, how do you run these quantum machine learning models? Because data is typically classical. How do you deal with that problem? How do you map it to the classical, and how do you deal with that? So, and I will just say that if you just want to understand about quantum computation slightly more. Where is this quantum, as we look at AI, where the AI started. Similarly, the quantum computation journey started with this gentleman whom we love a lot. So he said, okay, he was like he was, I mean, he was studying quantum electrodynamics, and the problem was like that, and he was doing perturbation theory, and perturbation theories get really intractable at higher orders. Let's say you want to take your quantum electrodynamics perturbation theory to 4 or 5 order, the number of the diagrams starts increasing a lot. And now we would like to have a computer which can track these quantum calculations. The problem is right there. That's what Richard Feynman realized. Now, if he wants to do his quantum electrodynamics calculations on classical computer, they will not be able to do it. And we know those of us who have studied quantum many-body systems on computers, classical computers, we know that classical computers run into problem. They can simulate very small systems. Okay, so the problem, we cannot study quantum field theories, we cannot study quantum many-body systems, we cannot study most interesting phenomena in quantum physics on classical computers. And then what use are those computers for us if we cannot study? And then the more importantly, if we the quantum matter has a lot of interesting properties. It can solve many of our challenging problems of energy. It can solve our, like, as we are nowadays looking for solar energy, we are trying to solve our energy problem. I mean, quantum matter has that potential that it will solve our problems. It will solve many of our healthcare problems and many other problems. But the problem is that we are not able to study those quantum nature. We are not study to quantum matter or any quantum bigger quantum physical system. We are not able to understand them classical computers, and that is why Richard Feynman is recommending and motivating us that we should look for alternative machines. And that's why nowadays that race started, that we should build the quantum computers, if not for some other reason, definitely to study quantum physics, quantum matter. And because once we have the control on quantum matter, we will be in a different place altogether. Okay, and what is the important thing? What is the main difference between classical and quantum computation? It is this property which you study in quantum mechanics, is called quantum entanglement. Now, when you look at the quantum entanglement, many people start looking into Bell inequalities. People start looking into many different aspects of quantum entanglement. It's a very interesting non-local property which quantum systems have. But in quantum computation, we took it up from a different point of view. Quantum entanglement in quantum computation is called a computational resources. Like as you have memory, like as you have a processing power, like as you have some other parallel processors and all that, they are computational resources for you. Similarly, quantum entanglement is not just a weird property of quantum matter, rather it's a computational resource. You cannot run many of those. Like as you take any quantum algorithm, you take quantum cryptography, quantum teleportation, super dense coding, your Grover's algorithm, none of those algorithms will run. Shor's algorithm, none of that will be possible without using quantum entanglement in those algorithms. So no quantum entanglement, no quantum computation. As simple as that. Okay, but without getting into the details of that, I think for an audience like this, I think you are already familiar with these things. Now, I just want to spend a minute in telling you, if any of you is interested in getting involved in quantum computation, because quantum computation involves two things. You have to talk about algorithms and all that, then it's an implementation also. Now, where are we in terms of implementation? You see on the left side of the slide, there's a list of the places where you can do quantum computation, in quantum programming, so-called, because classically you use C++, Fortran, Python to do programming. In quantum computation, you want to do similar thing. You can use something called IBM Qiskit. Google has its own platform, Cern. Microsoft has QHash. Azure Quantum is also there. It has also Jupyter Notebook-like interface. Then we have Rigetti Forest, Xanados, Penelane, TensorFlow Quantum, and PyTorch Qiskit. These are some of the main which I am aware of, which are nowadays used a lot. So these are the quantum programming platforms where you can get started. And fortunately for all of them, there are lots of tutorials. I hope it shouldn't be so difficult to get started. Okay, now let's come back and let's ask one of the important questions. Okay, you will say, okay, I understand, this is all important, this looks interesting, and a lot of stuff is happening. But if I get interested in it, in this whole thing, what should I do? How did I get started? How should I get started? So I will on the left side, I have given you some of the prerequisites, and fortunately, you will realize you are more or less familiar with most of these details. You know mathematics, linear algebra, multivariable calculus, little bit of optimization theory, which is that maxima minima theory, which you would have studied sometime in calculus. Then from statistics, you need to know probability theory, regression, correlation, distribution, and some bit of a Bayesian probability theory as well, because that gets used a lot in data science. Similarly, you need a bit of a programming experience. I would say a beginner programming experience in a language like Python. Definitely C++ and other, it will be definitely advantageous, but it is good to have some experience in Python. Okay, and I have also put this very interesting slide there just to tell you why should you become data scientists. And I found interesting here. It says that by 2026, the world will need 11.5 million data scientists. This is huge, fine. And I think that itself should give you a kind of a sense what is the job market going to be like in few years from now. Okay, I think I will stop here my presentation with these three important quotes, which have been, which have reshaped my own understanding about the world and how should I proceed in my own career. So this is first quote is from Archibald Wheeler. It says it from bit, I think, which says that you can take a information theory point of view in understanding that Archibald Wheeler was the person who got information theory very close to physics. And then there was a big discovery, I would say, from Rolf Landover, who was also working with IBM. He said he came up with this immense and deep understanding that information is physical. And this is a huge thing, because what it is being said, the data which you are talking about, the data in the data science, that data is also, it's not the model is mathematical and physical, the data itself is physical. Okay, and then the last quote is as we see is from our pioneering quantum physicist and quantum computing physicist. Is he says this is really a very powerful statement. It's called, it has a name, it's called a Turing-Deutsch principle, not just thesis, it's a principle. It's a physics principle, like as you have a principle of conservation of energy or any other principle. It says any physical process, classical and quantum, can be simulated on a universal quantum computing machine. So everything which you understand, the whole physical world can be understood by a universal quantum computing machine. So that's why there's a need to have this quantum computing machine available to us, because once we have it, we will be able to understand the whole physical world, which is not possible as of now, because classical computers can help us understand the classical part of it, but not the quantum part of it. So I will stop there, and thank you very much for having me for the session.
Thank you very much, sir. Thank you very much. Sir, we have a few questions from the participants.
Yeah, sure, Nikhil.
So first question is from Vikas Dhaya. Where should the students start to learn quantum computing, especially those who have not been from quantum background?
Okay, so so there are many courses which are available. I would because I come from IBM, so I would definitely, my prejudice will be to suggest the IBM website. IBM has because IBM's platform is very user friendly, and there are lots of tutorials. There is a university level textbook which is called a Kiski textbook, and if you go to that Kiski textbook, you will see not only the discussion about the basics of quantum computation, there's an implementation also available, and then there are references from that. Okay, because typically I have seen many people go and they take this book by Nielsen and Chong. They think they will master Nielsen and Chong, they will do quantum computation. I would strongly discourage that. I don't. You guys should not get trapped in that. That book was written many years ago. That surely is one of the bibles of the field, but that will not get you started in quantum computing. Do not get into that mistake. Okay, take a simpler starting point. Take and try to run whatever you do, whatever you learn, try to do implementation, because quantum computation has this implement. It's about programming as well. It's not about just something about gates and then you are done. You are not done unless and until you implement. So you can get started with IBM. Then if you allow me also to highlight what we are doing in Kashmir here, we are also running a quantum computing course which is active as of now. If you are interested, you can take that as well. If you are not interested, you can still find many online courses which are available on YouTube. Cern also recently, maybe a few months from now, the Cern also ran a course on quantum computation. I think it should be available freely on YouTube. Similarly, there are other, I would say one of the best places would be John Preskill's lecture notes. But the problem with those biggies is that they get intimidated after a few lectures. You just lose the track of whole thing. So I would say there are lots of online resources available. You can get started. Then also you can get in touch with what you mentioned in the beginning. Kimmers is making one of our motivation is to bring quantum computation to Valley. Any person who is here in Kashmir, they should get easy access to quantum computation.
Thank you, sir. Sir, next question is from Shahid Altaf. That's a funny question. Can artificial intelligence escape the human control in future?
Human control. No, Shahid, just be ready. It's going to be very scary. Reverse will happen. Reverse will happen. What artificial intelligence is going to do, it's going to eliminate the human control. Okay, so that's what people like Elon Musk are kind of afraid of. Anyways, I mean, this was I don't think, I mean, we should I don't know what the where the question is coming from, but humans will be always there. Something called a human in loop. We will be in control of AI. This is going to be, you can think of it as some sort of a symbiosis between neural networks, AI, and humans. Okay, and I think that's what is going to happen. Yeah, but maybe I will have a separate discussion with Shahid.
Okay, sir. Sir, next question is from Sajid Mohammed. How moving to quantum neural network will solve the data training issue for machine learning?
Yeah, because you can think it this way, friend. You see what quantum computation means. It always means, the basic thing what it means is that more computational power. Let's say if you use classical computer, if you have to use 10 different computers in parallel for the same thing, you can use the same quantum computer. No parallelism, no parallel computers are needed. It will mean more processing. So let's say you have let's take the Cern data, which was in petabytes. If we have access to quantum computers, we can load this data into quantum qubits, which is the quantum encoding piece. And qubits, by the way, hold a lot more information than classical bits. Classical bits like just two-dimensional thing, fine? Two-dimensional space. You can just have either in 1 or 0. In a qubit, you have a huge space where you can store your data, and then it can be processed much faster than that. That way, it will be able to solve the problem. Not only training, I mean, other problems as well.
Thank you, sir. Sir, next question is from Mudassir Malik. AI has shown biased character too in its chronology. How to deal with the stuff like algorithmic prejudices?
Yeah, I think it's a good question, Mudassir. Yeah, definitely. Because see, there is this kind of a theorem. I mean, the way AI learns, the AI neural networks learn. You give them the data. It's called a garbage in, garbage out. Let's say if you give data which doesn't have information, you pass it on to neural network. Neural network is not going to learn from it. So the data, the kind of data which you are giving to the neural network is going to be important. Okay, that's one thing. Then there is something called, there's another area in artificial intelligence. It's called AI interpretability or AI explainability, which makes sure that if any sort of prejudice that has gone because of the data, any sort of prejudice that has gone into the learning, we deal with that prejudice at the end of the end of the calculations, or maybe in the beginning itself, because we should make, it's called algorithmic fairness. We will, there are ways nowadays, people are, no, there's a lot of focus on this thing, because let us say you have clinical data or you have some legal data, and you pass on that legal data through a neural network, and it gives you some results which may have implications, serious implications. So people in AI are aware of these things, and there are methods which are being applied to deal with it. But I think it's manageable. It's not like it's something an uncontrollable problem and we will not be able to deal with it. It's an important issue, and people are able to deal with these things in the area of something called AI interpretability and algorithmic fairness as well.
Okay, sir, next question is from Basit Iqbal. Do we need to study machine learning for studying quantum machine learning, or to study neural networks?
Sadly, yes. Sadly, yes. Because quantum machine learning is machine learning, but you are doing it using quantum computers. Otherwise, it's machine learning. Quantum machine learning is solving your machine learning and AI problems using quantum computers, which means you have to, as I said, you have to somehow participate in that happy marriage between AI and quantum. you have to be part of that.
Okay, sir. The next question is from Latif. Machine learning can bypass the laws and known theories to predict the time evaluation based on experience learning. How is it going to change our teaching and learning research in physics?
No, I didn't get the first part, whether it is going to, what is it? Can you, sorry for
Okay,
that.
sir.
Can you read again? What
Machine
is
learning
it going to
can
bypass?
bypass the laws and the known theories to predict the time evaluation based on experience learning. How is it going to
No.
change our teaching?
I don't know the first part. First part, I can't comment. I don't know about that part. But second piece, where he's saying about the education, I think yes, it will. It is going to make our no AI is going to make our classroom smarter, because it's going to. It's like this. I will just give you just one example, which I myself have developed. Like, as typically we use it to build these charts. Fine, you have data, you plot it, you get a chart. Now, what is possible nowadays, you can interact with that chart, like as you interact with your Google now. Okay, you can know you have data. You will there will be there will be a program, a neural network based program. It will plot the data for you, and it will plot according to your commands. You will tell him, okay, I have the data, I want to this particular axis plotted this way. Okay, and it will plot whatever information you want to extract from that data. It will dynamically interact with you. Fine. And then we can use AI. I mean, it will be a separate discussion about how we can use AI in education. I myself have a lot of interest in that direction. How can we make it education? Because education is one and that particular critical sensitive area where we should bring these technologies and make a larger impact. And AI surely is going to make an impact on that. But this one, I just gave an example how you can make interactive kind of a interactions between students and the study material. Okay, I mean, students will surely like to video interact or audio interact with the material, so that it becomes non-static and boring stuff. It becomes more interesting. That thing we can surely do for education.
Okay, sir. Sir, next question is from Bhatt Muzammil. Why quantum processes have to be carried out reversibly?
Okay, so no, they don't have to be carried out reversibly. The difference between classical and quantum computation is quantum computation is irreversible in the following sense. I mean, you do a gate. Let's say you applied a C naught gate. I'm sorry, you applied a NOT gate. You cannot reverse that gate in classical computation. In quantum computation, gates are unitary transformations, and unitary transformation by definition is invertible. It's you always have an inverse for a unitary transformation. So that's why it's reversible. So if you do it quantum computation in one direction, you can reverse the whole thing and get back in the another direction as well. It's always possible to reverse. That's in fact one of the big advantages of quantum computation, that it's a reversible quantum computing.
Okay, sir. So next question is from Sadat Sheikh. He says, thanks for the interesting talk. AI is indeed very promising, but could you also delineate about its ethical issue that are arising very fast, such as deep fakes, human bias? How do you think these issues could be dealt in future as an expert of AI?
Yeah, thank you for that. I think so. Definitely, no, there are this is related to earlier question which some
Yes,
of our
sir.
friends asked. One of our friend asked. So so that there are. I mean, it's the people in AI are aware of these things, because let's say if our neural network is biased, it's a problem for everybody. It's not a good thing to have a biased AI. Okay, but the bias itself comes many times. It will come from the model, but mostly it comes from the data, the kind of data you have. Therefore, there are another set of AI tools which are being built to make sure that there's a algorithmic fairness in our models, and the data, the way we use it, there's a some sort of a I would say balance. We try to balance that thing. So that part is already there. Okay, now there is an extra piece which is said, which is about deepfake. So deepfake is just coming from one particular neural network architecture, which is called a GAN. Okay, generative adversarial network. I think we will be able to deal with that. It is not, I mean, let's say we take a GAN, it produces a deep hack. My guess is that it should be possible to devise another GAN model which will be able to detect that it was a deep hack. So I don't see deepfake as a problem, though as of now it is being used to do a lot of fake news is being created, and we see on social media a lot of kind of mixture and deepfakes are being used to spread the kind of bad news. But I'm sure we will be able to. It is not a technical challenge. That's my guess, because we can kind of counterbalance it.
Okay, sir. The next question is from Hilal. What is the best platform to simulate quantum circuits?
IBM, IBM Qiskit.
Okay.
So there is an IBM Quantum Simulator. You can go there and you can do that. But yeah, definitely. I mean, depending on you, what do you want to do? My first choice would be IBM Quantum Simulator. But if you are not happy with IBM Quantum Simulator, first of all, tell me why you are not happy. I will take that as feedback. But secondly, there are other places also. You can go to the D-Wave. I don't know what kind of quantum computation you want to run. But there are other platforms as well. There are other simulators which are available. I think D-Wave also has, for if you want to use for annealing, they have also available. And I think there are more simulators from, I mean, that Hilal can get in touch with me. I can tell him many more which he can use.
Okay, sir. So next question is from Sajid Mohammed. How will you
Mhm.
know if the problem you are trying to solve requires more nodes in a neural network or more layers with some number of nodes?
Okay, so no, that gets like no decided when you, let's say I started with a definite number of nodes or these layers in my neural network, and I run this task and I see what is the accuracy. There are always something called error metric. If my neural network with that number is doing good and I am getting good accuracy, then I'm happy. If I am not, then I have to change. These are called something called hyperparameters. Then I have to change my hyperparameters. It will automate. I don't have to do something physically. It will automatically change the number of nodes in each layer, or it will change the number of the layers itself, so that because the end goal is to get a good accuracy. Let's say I am doing a computer vision problem, and no, I am using a neural network. What I want to do, that computer vision classification problem, my neural network should do well on that problem. So how do I do it? Start with the architecture, take some hyperparameters, take parameters, run the model. If it is giving good accuracy, we are good. If not, then change the hyperparameters and get to the accuracy.
Okay, sir. Sir, I think we are done with the questions. I have a few questions, like basic questions, you can say. Language translation generate data. Is all the data collected by Google? Like we have AI like Siri and what we call it, Alexa.
We Alexa, Siri is there. Google has Google Assistant itself.
Yes, sir. So that all data that we like say there, that all data is collected by Google.
Okay, so what it work the way it works, Nikhil, is that you have, as I said, it takes input. Let's say when you start interacting with the Google Assistant, okay, it takes your voice, fine, then it converts it into text. Then behind that there's a model which we call as pre-trained model. In language
Okay.
processing, typically we use always pre-trained model, and that pre-trained model is being used to for that speech recognition purpose. Okay, so I mean, there are two pieces. The data, that particular time, the data which we use, like as I use my data, I say play this song for me. Okay,
Yes,
it
sir.
takes that voice, then it tries to understand. How does it try to understand? Because it has already a pre-trained model which would have taken those voice, like as play this song. These are like usual words which we use, and Google already has the kind of a representation. It has already run this model on these words, so typically it automatically understands. But there are two pieces to it. One is speech to text. It makes it a text first of all. Okay, your voice gets picks words from that and they get translated to text. On that text, then there's an NLP language model which runs, and that's how it basically picks it.
So, but they like actually store that. Like I have played a song. I have asked Alexa to play a song, so that the storage that is stored somewhere.
Oh no, the song comes from you, or no, wherever you wanna do it. It will be linked to somewhere. Let's say you wanna link it to YouTube, then it comes from the YouTube. Song is not stored. Song is somewhere
No, sir.
somewhere
No,
there,
sir. The
maybe.
information that I have played this song.
Uh, Okay. Yes. See, I mean, without getting too much into the language model detailers, see what is happening whenever you have a language model. Okay, the way it works is that for every word there is actually there's a vector, and that model should understand what vector it is. For every word, there's a vector in that language model. Let's say I say, Google, Alexa, can you play this song, or can you show me particular picture? Okay. So what happens is that there is a vector for that model, and that it automatically identifies that model is there, which identifies that word. It understands what is to be done. It takes the action after that.
Okay, sir.
By the way, Nikhil, I myself developed these. I mean, one of my thing was I developed this particular thing. It was not interacting with the video data. It was not interacting with this YouTube videos. It was interacting with the data, like which you plot. What it was doing, it was taking the voice, and it was converting it into text. That text one then was doing something behind the scenes, and then there was an action was taken on that plot. Let's say I will tell it, can you plot speed versus something for me? It will do that. I will next time I will say do something different for me. It will do something different for me.
Okay, sir. Okay, sir. Sir, like we have our data in Google Drive and all, like where that data is stored. Like we say that we have stored our data on our mails and Google Drives and Google Photos. Like where does that data get stored? Okay, sir.
No, it gets stored with it's with Google. It's with Google itself. It gets stored in their servers. They have their data centers. I think it gets stored there.
Rukhsar.
Hello. Assalamu
alaikum. Rukhsar, assalamu alaikum.
Walaikum salam. Ashraf sahab, kaise hain aap?
Good to hear. Good to hear. Good to hear. Very good. Very good. So I was listening to all your talk, and then I'm also fascinated. I have been requesting my colleagues as well as my students, these young students. We have started master's program, that we should take a lead in NIT Srinagar in going to data center and then to artificial intelligence. So many people from the valley are coming that we need a guidance in artificial intelligence. So throughout the institution, we don't have the expertise in this. And in data science too, we don't have an expertise. Machine learning too. So this is really good. This is really good. Once the things settle down, please do visit us. Be here for a couple of days, and then see, identify the people. You are a visionary. Identify the students who can take a lead in it. We can send them for training program for 15 days or a week's time for learning these data sciences and then the artificial intelligence. I have always believed that physicists should take a lead.
Right, sir. Yes.
What you are saying, that you have done things good as compared to your competitors, as compared to your colleagues, because you are knowing the physics. So
yes, true.
My sincere suggestion is, my sincere request and then invitation is that you please do come once these things settle down within a week or so, or after 2 weeks. Do come and identify few students whom we can depute for this artificial intelligence and then data sciences.
Yeah, definitely. So, Ashraf Saab, if I have to say, I think it is not only is it in industry, it is trending.
Yeah.
Nowadays, the way physics is being done, people are using in condensometer, for example. Not only condensometer, I gave example from LHC experiment. There you cannot do stuff without machine learning. It's everywhere. Nowadays, the way people do physics is with machine learning and deep learning. That's the kind of a trending way of doing it.
Yes. It's really good. I'm thankful that you did a very nice talk.
No, the only thing is that I would have really loved to meet you all in person, but it didn't happen this time.
No, I was talking to Prince Saab also that he should have been in person here. But the thing is that, that situation is altogether very bad. Tomorrow we are supposed to inaugurate that one of that biggest interval event of international conference, 7th of this April, which was scheduled from 7th of April to 11th of April. But we postponed that even. So it has gone to September. It has gone to September. So the vice chancellor of that one, the vice chancellor of Mahatma Gandhi University was making a call in the early morning. Sir Shah, tomorrow I have a lecture. I said that we have postponed, sir. So we have postponed that event. So within a week or so, or after 2 weeks, I will request Rubabji also to invite you formally. Sit down with us for a couple of days, and then we need people who can work in data sciences and artificial intelligence, so that not so much, even including that education department once requested me that you spoke on that artificial intelligence. I said that no, I am not. But one of our early directors, who was the first director of NIT Srinagar, though an old man, probably 80, 82, with his hard work and dedication and then patience, he is working. Professor Ali Muhammad Wani, working in Central University, he is doing that artificial intelligence now. So I want really few students of ours should work in this artificial intelligence as well as in data sciences.
Right. No, sir. I mean, if you see other universities, like as I think many places like as BITS Pilani, IIT Madras, they have already started. I mean, people realize these are important areas. So I mean,
already.
I think you, if you can talk to NIT director, I would suggest every place in Kashmir. We should talk to Kashmir government as well, and we should get these things started here, because this is no, as I was saying, 5 years from now, people will say, no, it's not like, I mean, I remember earlier days, there used to be these subjects, zoology and botany. Then biotechnology came. Everybody ran to biotechnology. Now, if you have done something in botany, they are saying, वो लोग सोच रहे हैं अब हम कहाँ जाएं? ठीक है? Because everybody is doing biotechnology, biochemistry, biotechnology. Same thing will happen 5 years from now. Everybody will be an expert on data scientist. और जो नहीं है, they will say, अब हम कहाँ जाएं?
Yes.
It's as serious as that.
Really, I can understand its importance. I can understand, and I can realize it. Believe me, we are entangled with these families. Otherwise, I would love to jump into this one. Since I have jumped in nanotechnology, I would love to jump into this. Believe me, yeah. Even so, nobody does, I'll start doing. At least we can give a guidance to most of the people, most of the children who are working outside. They come to NIT Srinagar. We want a guidance in artificial intelligence. We want a guidance in data sciences. So I am referring them that IIT Madras has a specialization.
Right. No, sir, I will come down. हम बात करेंगे इसके बारे में. I think it shouldn't be too difficult to set up such a program. मुझे नहीं लगता है कि it's like rocket science की नहीं होगा. We should be able to do it.
When Professor Ali Muhammad Wani could do it, he was basically from an electronics, an intelligent professor, who was the one who was appointed over here as an associate professor directly. Then was a principal and the first director of NIT Srinagar. And believe me, I was so happy that he was guiding his students in artificial intelligence in Central University. Probably he's the only expert over here.
Right. Nice.
Okay, carry on. Niklesh, carry on.
Thank you, sir. Now to conclude the session and for the vote of thanks, I would request Dr. Sameem Rubab ma'am to say a few words. Rubab ma'am.
It's indeed our pleasure that Rukhsan ul Haq, our I would say a colleague, a student, a friend of our department has joined, and the talk was really nice and interesting. It was very useful for our student. And one last question has come from a student who sent to everyone. What are the career opportunities for the physics students in developing the hardware like quantum chips for quantum computing? So this is directed to Rukhsan.
Yeah, okay. Yeah, I think this is also a nice question. I mean, I forgot to mention it. There are many opportunities, because quantum computing means two things. One is definitely I focused more on algorithmic part of it, but then there are a lot of developments happening from the hardware side. Okay, and I would say most of the work as of now, like as I mentioned, in IBM is planning to build these many chips. That plan is about hardware development. It was not about software part of it. Similarly, there are many new. IonQ is a recent kind of entry into the hardware piece of it. So I would say there are many for experimentalists. There are many chances. Let's say people are developing superconducting qubits. They are developing maybe magnetic qubits as well. but most is towards ion trap based qubits as well as superconducting qubits. But there are many opportunities, I would say. And I think if somebody is interested in getting in touch with somebody in IBM in terms of what they are doing, manufacturing work, I have some friends in hardware as well. Maybe I can put them in touch with them so they can try to understand better what can they, how can they get involved in quantum hardware development.
Thank you, Rizwan, for this information, so that some of our students who are really interested in developing some hardware, so they may contact you and you can put them or suggest them the right person. And really, it was a very interesting and futuristic talk. I would say I got to learn so many things. And I would like to inform my students that all of you, the MSc students, may not go for research in physics. Some of you, if you wish, you can directly switch to data science by joining some courses like IIT Madras is started, and then there is a data science master's program in CMI also, Chennai Institute of Mathematical Science. They also have a program in quantum computing, data science actually. And if you search, you will get things if you really wish to join. So indeed, it was a very pleasant, I would say, morning session with you. And uh, thanks from our students, our HOD, from me on behalf of our entire department to you. And Rukhsan, we can have a informal gathering maybe next week or next to next week when you come around. Like we can meet, you can meet with faculty, because large gathering is prohibited, but meeting in a small group, say 10 people or 8 people, is not prohibited. So any day if you wish to come, then you inform me and we will arrange a meeting with faculty. So with that, I think there are no more questions from the audience. So I would thank you once again and would like to conclude the meeting from our side.
Thank you, ma'am. It was I really it was really nice, and I just hope that it was useful to the student community.
Yes, it was very interactive session, because usually students don't ask questions, but they have asked plenty of questions and they were satisfied. You have given answers to almost everything what they have asked. So I think it was a very useful session. It was dynamic and participation was also, I would say it was a good participation, around 50 all the time.
Sir, if
So
you allow,
thank you so very much for joining us.
Yes, yeah, Nikhil.
sir, if you allow me, I would like to ask one more question.
Yeah, sure, Nikhil.
Sir, in your presentation, you discussed about teleportation. Sir, what do you mean by that? Like, what teleportation kind of thing we are talking about?
ये वो वाली नहीं है, Star Trek वाली नहीं है. If you have
Okay.
watched the Star Trek movie, then it is not that. Teleportation basically means, I mean, because in science fiction, they will tell you that you will take somebody and teleport it somewhere else. तो quantum mechanics या quantum computing में ऐसा नहीं होता है. तो it is like, मान लो जैसे कि आपके पास एक quantum state है एक जगह, और आप what you wanna do is that you wanna send it to someone else. अब quantum mechanics में ये problem है कि आप उसको copy नहीं कर सकते हो. जो आपकी quantum state है उसकी हम copy नहीं बना सकते हैं. This is no cloning theorem in quantum mechanics, है ना. तो what will we do? अब हम क्या करेंगे ना, that there's a protocol, एक तरीका बनाया गया है कि आप एक अपनी quantum state को एक जगह से दूसरी लैब पे virtually, actually, let's say someday I imagine, dream, we will have a quantum computation laboratory in Kashmir, in NIT, for example, and you want to send your quantum state to your colleague जो दूसरी जगह पे है, थोड़ी सी दूर जगह पे है. But what you want to do, आप उसको कैसे करोगे? तो teleportation वो एक प्रोटोकॉल है. आप कुछ चीजें करते हो अपनी लेवल पे, कुछ एक्सपेरिमेंट्स करते हो, then your colleague, she will do something on her side. Consequently, what will happen is that your state, quantum state जो तुम्हारे लेबोरेटरी में प्रिपेयर की गई थी, वो वहां तक पहुंच जाएगी using that protocol. So it's like quantum information is being passed on, or quantum states are being passed on, not any physical object.
Okay, sir. Thank you, sir.
Yeah, thanks. Thank you. So thank you. Then I think I will drop now.
Okay, sir. Thank you, sir. Thank you very
Okay.
much.
Okay. Bye. Bye, everybody.